Hi, this is Mr. Matthews, and this is our notes on bonding and water. We're going to start with a little bit about chemistry. Why is chemistry important to us? Why do we study chemistry? What's the usefulness in biology? There's a whole separate other class called chemistry, which you'll take next year or in future years, and you'll learn a lot more in-depth things about chemistry. But we just want to start with sort of the importance. And mainly why we study chemistry and biology is that chemistry has to deal with matter. All living things are made of matter. And we talk about metabolism. That involves breaking down bonds and molecules and chemical interactions between certain things to get energy or to break apart ATP for energy. And so we have that process that's very chemically involved. Um, Matter, just going to matter. Matter is everywhere. And we're going to define just a few terms. Again, just some basics before we move on to water specifically, but just some basic chemistry terms that you need to know. Matter. If you've not heard of matter before, every living, non-living thing is made of matter, and matter is made up of atoms, right? And all the elements that we've talked about so far in class and that we're going to continue to talk about in the future are all composed of these elements, and these elements bond together to form molecules, and molecules bond together to form compounds, and this is what makes up living systems. So getting to know the atom, and you had these words in your word inventory. You have an atom, and the neutrons have no charge in the middle. The protons are positively charged, and the electrons are on the outer shell here, and they have a negative charge. And just looking at these periodic table of all the elements that we find on the planet, every element has a different number of protons and neutrons, and some have a charge and some don't. So take your pick. We have 117 elements. 25 are essential for life, and of those 25, 4 make up the 96% of what's found in living matter. Now, I asked you previously to know, these six. Know these six: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, CHNOPS. You need to know those six. 4 of them make up 96%, and the other 4% are primarily composed of phosphorus and sulfur. Calcium, potassium is obviously important, but really, CHNOPS is something that you should be well aware for this particular unit. Just going back to an atom here, what is a charge? What are electrons and what are a charge? Electrons are found in regions around the nucleus in different levels. You have first shell, second shell, third shell, and they contain a certain number of electrons that are negatively charged. And the octet rule is that atoms tend to lose or gain electrons. So to have 8 electrons in the outermost shell, and if you count these outer rings, 2, 4, 6, 8 in the outermost rings, and that's where you gain and you lose your electrons. And gaining and losing, that's how we also form bonds. So looking at some chemical reactivity, atoms tend to complete or partially fill a shell, whatever's available, they want to fill that, and empty a partially filled a valence shell. So looking at having a full or not full valence shell determines whether an atom is not stable. These chemical bonds are formed as atoms try and fill their shells. Here you have hydrogen gas, H2 is what we call it. You can see that you have the electrons that are filling the outermost layer there. Chemical bonds are just the force of holding two atoms together. Just going back to what a bond actually is, I think this is in your notes that atoms really want to have those outer shells of electrons filled because it makes them stable. They stop moving. And atoms can lose or gain or share electrons to become stable. Everything wants to become stable. So filling that outermost layer is really, really important for atoms when they're moving around. And of course, these bonds that form have some really important biological implications, which we'll talk about in just a minute. So just the bonds we talk about in biology, the weaker bonds are hydrogen and ionic bonds, and the stronger bonds are the covalent and polar covalent bonds. So let's start with the covalent bonds. Covalent bonds, why are they strong? And the answer is they share a pair of electrons. Two atoms share. They're sharing electrons. They're both holding on to the electrons, and so they tend to form molecules. Molecules are more than one atom. So you have H2 here, which is hydrogen gas, and you have H2O here that are forming. So this is a really strong bond between the hydrogen and the oxygen. They're sharing electrons, and And primarily, if you look at just the shape of water here, oxygen and two hydrogens, we call water as like a bent shape right here. That actually has some important implications when we get to surface tension and cohesion and some of these other terms about water. But covalent bonds are just when electrons are shared and you form a bond that forms molecules. Polar covalent bonds, if you want to take that a step further, is not only are you sharing electrons, but you're getting the charge on each end of the molecule. So a pair of electrons that are shared unequally by two atoms. If you look at oxygen and hydrogen, they don't have an unequal amount of electrons. So the sharing is going to be unequal. So water is hydrogen and oxygen. And again, oxygen has a stronger attraction for the electrons than the hydrogen. And so water is a polar molecule because you end up having a negative charge on one end and a positive on the other. And this leads again to some of this forms a bent shape. And this really has so many interesting properties of water. The ionic bonds are just attraction between atoms with opposite charges. So an ion is something that has gained or lost an electron, has a charge. And we often find these bonds are fairly weak. Something like table salt is a very common ionic bond. It generally is negative. So we have here as a picture, we have our sodium that loses an electron and bonds with the chlorine, positive and negative. It's a really weak bond between the two. And we'll get back into that formation in just a minute. But let's take a look at hydrogen bonding. Another really weak bond, a weak attraction between water molecules. I have my bottle of water in front of me, which you can't see, but you can hear my water shaking right here. And what I'm doing as I'm shaking my water is that the water molecules, these hydrogen bonds in liquid water are, when I shake it, they're constantly breaking and reforming. I mean, if they weren't able to break and reform, then we would have ice. But because the bonds are so weak, we can actually move water. But again, this is the weakest type of bond. And we'll see hydrogen bonding pop up later on, especially when we talk about DNA. But really a pretty weak bond. The positive hydrogen in one water molecule is attracted to the negative in a other molecule. And that's generally how we get liquid water to form. We very rarely see just one water molecule. You see in this picture here, the hydrogen of one is bonded to the oxygen of another. Because that attraction from the oxygen is just so strong. But these are pretty weak bonds that continuously break and reform. And again, just going, why water? Why is this? How does this deal with water? We want to really talk about these properties of water. Water is the foundation of life. I mean, nearly 70% of your body is composed of water, and about two-thirds of the molecules in your body are water molecules. Your cells, your blood, everything is filled with or surrounded by water, and it's what sort of transports everything in and out of your cells and to the tissues that need certain elements. So just looking at the chemistry of water again before we move on, just the structure of this water molecule, you have it's polar. Water is polar. It's a bent shape. It has positive and negative poles. The electrons spend more time around the oxygen than they do the hydrogen. That's a negative side of it. And so this formation, this concentration of that charge makes it a sort of a bent shape. And again, we have the covalent bonds between the hydrogen and the oxygen. And then when we have two water molecules that are bonding together, that is the hydrogen bond. That's really important in like surface tension and cohesion. So again, looking at this hydrogen bonds between the water molecules, again, it creates a really sticky molecule. So you have the hydrogen of one is bonded to the oxygen of another. And these are constantly breaking and reforming, constantly breaking and reforming. I'm breaking and reforming them right now as I shake my water, if you can hear that. But why is that important for life? What does that have to do with, why? The importance of water. So when we go over these, just really note the biological importance of these properties and how the property is related to water's polar structure. Having that oxygen being negative, the hydrogens being positive, and you have this charge on both ends. And based on that charge, you have covalent bonding within the molecule itself, and then the hydrogen bonds that form within the water molecules. Think about this polar structure and how it relates to the biological importance of just life. So we'll start with the storage of heat. We often call this specific heat. And by definition, specific heat is the amount of energy needed to raise a 1 gram substance 1 degree Celsius. And I'm not gonna have you memorize that, but you just need to know that it really does take water a long time to heat up. That's what we're really talking about here. If you put a whole thing of water on your stove, cooking spaghetti, for instance, it might take a long time for that water to heat up. And so we say water has a high specific heat, and this is really due to the hydrogen bonding. Water wants to resist these temperature changes. They're constantly breaking and reforming. You have water that is boiling, that just starts to move. It takes a lot of heat to heat up this molecule, and then once you've heated the molecule up, it takes a long time for that all these bonds to stabilize and for it to cool down a little bit. So looking at the biological importance, number one, water is really moderated by temperatures on Earth, right? It actually, sorry, water moderates. It's doing the moderating of the temperatures on the planet because it can withstand a whole wide range of temperatures. It takes a long time for it to heat up, and it takes a long time for it to cool down. And this is why we're able to live in different areas. I mean, we can step outside on a hot day in the summertime, and we don't have to worry about our blood boiling. We can actually, be able to take a while for our body temperature to heat up before it really becomes, too much for us. And that's why we can step outside in the wintertime too and not have our blood literally freeze. So it just takes a long time for water to heat up and to cool down. So another important reason for that, this specific heat, water's evaporative cooling. Many organisms release excess heat energy through water evaporation, sweating, and that's what we do when we sweat. We're releasing some of this excess heat. Water helps maintain homeostasis. Homeostasis is just maintaining a balance. So we release that energy through the sweat, and of course, if we're moving, if we are breaking chemical bonds, oftentimes energy is released. So if we're outside running on a hot day, we're using a lot of energy. We're breaking a lot of bonds to do this movement, to run around, to do whatever activity we're doing, and so our bodies naturally have this excess heat that just needs to get out. So we get rid of that heat through sweating. Cohesion and adhesion. Here we have a little water bud there. And cohesion is just attraction between substances of the same kind. Cohesion, the same kind. So hydrogen bonding between water molecules creates cohesion. So just staring at a glass of water, you have water that is sticking together, and then you have surface tension. That's why bugs can float on water. That's why, if we haven't done so already, we're going to have a little competition to see who can actually get a paper clip to float on water. But cohesive properties are really, really important for what we often call capillary action. If we've not talked about that yet, we will. Adhesion is the opposite. This is the attraction between different substances. So you might have water and a straw. So that attraction between the water molecules and the straw, as you're kind of sucking it up out of the glass, that is adhesion. And that's important because if you're trying to move water up, you have gravity that's trying to keep it down. So you have not only when you're sucking something up through a straw, this is a lot what capillary action is, you have the attraction of water molecules together, which is cohesion, that's enabling you to have a column of water to come up, but then you also have the attraction between the straw itself and the water molecules. So the two together are able to make water go up through capillary action against gravity. So we have a meniscus. If you've ever looked at a graduated cylinder, you have that like little meniscus curve on the side. That's cohesion, the attraction between water molecules and that graduated cylinder. Water climbs up fiber. Okay, so if I dip a paper towel in water, water's gonna, we say, soak it up, and that's really what adhesion, that attraction between water and the paper towel, is really an important concept. So again, this importance of capillary action. So plants naturally lose water. Water gets evaporated through their leaves. That's called transpiration. So as the water gets evaporated, the roots kind of suck up more water to the leaves, and this sucking up is it's a straw-like vesicle, sucks up the water towards, up against the gravity, and so this column of water that's coming up through the roots has to stick together to get to the leaves. So cohesion, the water molecules stick together, and adhesion, the water molecules are actually attracted to the sides of the roots, and the water is able to get from the ground to the plants pretty quickly. Polarity, again, just looking at polarity, having that positive and negative event. And this is really important when it comes to dissolving. You have salt here. Salt is, sodium is positive, chlorine is negative, and the water is a good solvent. It's also called the universal solvent. And when we say dissolve something, it just means that water is able to surround and gets attracted to one of the ions that is in the water. So water is able to literally break apart that ionic bond and forms a separate bond, sodium chloride, and that's what we say dissolving in water. Sugar is sort of the same reaction in water, but because of water's polar properties that allows it to break apart the ionic bonds. Of course, the important, polar molecules dissolve well in water, and this allows water to transport materials throughout our body. Anything in and out of our body. Nonpolar substances like oil, or lipids, they are not attracted to water, so that's why we see oil beads in water. And the importance of organisms. Why is that important? And we'll really get to that when we talk about the cell membrane. Having these nonpolar substances that make up our cell membrane that really control what comes in and out of the cells is very, very important. Last couple of things, pH. We've been working with a lot of pH in our class. pH stands for percent hydrogen. And the pH of a neutral solution, which is water, is 7. Acids are below 7. Bases are above 7. So just keep that in mind. I'll show you a picture here. Here's our pH chart. But really the biological importance is that many molecules and many organisms live within a really, really fine range of pH. And so if the pH is affected, then you have things like proteins that change shape, and it's what's called denaturing. We'll learn about that in a little bit. But the denaturing of proteins or enzymes make it difficult for chemical reactions to take place. And so just changing the pH by like maybe 1 or 2 units really can have some detrimental effects in nature. Most biological fluids are within 6 and 8. Right, the human stomach can reach about 2, and that's important because it's so acidic, and that's how we kind of break down what we eat. Again, here's the pH scale. If you want to take a look at some common things that we see, urine is 6, water is, and blood is 7, seawater is 8, milk is basic, and we'll be testing these. Acids have an H plus, and bases have an OH, and it just so happens that if you add an H and an OH, what do you get? You get H2O. So if you have a base and you want to neutralize the base, you give it an acid and it turns into water. You have an acid, you want to neutralize the acid, give it a base, and it turns into water. I'll go over this on the board if this doesn't make much sense to you. But again, let me see if I can draw on this. Can I? No, it's not going to let me draw. So we'll just ignore that. But just know that if you want to neutralize an acid, you give it a base. If you want to neutralize a base, you give it an acid. And in the end, you get water. H plus OH equals water. So you acids, bases, put them together, you get water. Last thing about water forms, most substances are more dense when they're solid. This is a little different in water. When we say more dense, that means that it's going to sink. But in water actually gets more dense as it cools, and until it gets close to freezing, it becomes less dense. So that's why ice floats. And the hydrogen bonds between all these water molecules form what's called a crystal loose structure, and that is what is less dense than liquid water. We want to take a picture here. We have the water molecules are a little more spread out as the water temperature begins to decrease, and hydrogen bonds are a little more stable, whereas in warmer water the bonds are continuously breaking. But again, the most important thing is that ice floats. It's one of the few molecules where the solid phase is less dense than the liquid phase, and that's important to life because looking at what lives in water, ice actually serves as a barrier between the cold air and the liquid water below, so it insulates everything so it doesn't freeze. So if we actually had water that froze, that means that lakes, rivers, ponds would all freeze from the bottom up, and that water would be exposed to the air, which means that it would freeze and sink, and this would continue until all the water is frozen solid. There's no insulation, and that every winter time, everything in the water would actually die. It would get frozen. So really important implications for how life works. What you need to finally end up with, you have a summary section. Just sum up in about 1 or 2 sentences what you feel this is all about, and the important takeaways of this information. What I always like to ask people is, when you look at notes or when you read a passage, so what? What does that mean? Take a couple of sentences to review. What does this stuff mean? How is this useful to even our topic of sustainability in the STEM Academy? But these are the notes on bonding and water. See Mr. Matthews with any questions.